You're sitting in front of a screen. And somewhere in the universe there's a black hole. Now imagine dumping your hard drive into it, along with all your photos, correspondence, projects you've been working on for a year. An entire digital copy of your life, flying away over the horizon. The question is, can it be recovered? Physicists have been debating this for 50 years. Some say the information is destroyed forever, while others say it's encoded somewhere on the horizon, in short-lived holes, in a hologram. This isn't philosophy, it's a conflict between general relativity and quantum mechanics. In the 1970s, Stephen Hawking made two discoveries. The first is that black holes evaporate. The second is that this radiation is strictly thermal. And thermal radiation doesn't remember what generated it. If two black holes have the same mass, charge, and momentum, they're indistinguishable. Whether a book fell or a metal ball fell outside, it looks exactly the same. When the hole evaporates, the radiation will carry away only the energy, but not the structure. Meaning the information is gone. But quantum mechanics says, information is not destroyed. It can become entangled, dispersed, become inaccessible, but not disappear without a trace. This is called the information paradox. And for half a century it was considered the main headache of theoretical physics. The smartest people on the planet proposed beautiful ideas. Information is imprinted on the event horizon. It goes into a parallel universe. It is embedded in the structure of space-time. But all these ideas have a common assumption. Information is a certain object that can be dropped, recorded, retrieved. But let's ask more simply, what is information anyway? Take the simplest thing in the universe, a single elementary particle. An electron, flying freely in a vacuum. It would seem that nothing could be simpler, but this electron is not isolated. It creates an electromagnetic field, it gravitates, it interacts with vacuum fluctuations. Each such interaction leaves a trace. In an instant, the state of the surrounding fields is no longer arbitrary. It is compatible only with one trajectory, only with one charge, only with one momentum. This is the minimal information trace. The environment has lost a degree of freedom. Previously, it could be anything, but now it must remember that an electron flew through here. Note that the environment does not store a copy of the electron. There is no small icon representing an electron. It stores a historical constraint. After the electron's passage, it became impossible for the electron to have a different charge, move along a different trajectory, or not exist at all. Information is not something added to the world. Information is something that has become forbidden. This trace is non-local. It does not lie at a single point. Field disturbances propagate, or re-emitted, and become entangled with one another. After a sufficiently long time, no local region knows the electron's history. But the entire environment is no longer compatible with alternatives. To erase this information, it is not enough to remove part of it. All correlations must be destroyed at once. And that is almost impossible. Now let's take a complex object, an atom, a book, a planet. The principle is the same, but the recording density is colossally higher. With more degrees of freedom, more interactions, more restrictions. Each interaction is another equation imposed on the past, a single equation that determines almost nothing, Billions of equations make the past unique, creating the effect of asymptotic uniqueness of the trace. By the time the object disappears as a local system, its information trace is already everywhere, woven into the fabric of the universe. And this trace cannot be dropped beyond the horizon, because it has never been in one place. Now we look at a black hole. For an external observer, the object's fall stretches to infinity. Time freezes at the horizon, meaning all interactions, all acts of information in the environment have time to occur before the object formally crosses the horizon. The substrate, mass, energy, charge, what the object is made of, disappears inside, but the blueprint from which it was built, all the unique correlations, all the restrictions remain outside. Information is not the same as an object. An object is local, while information about its structure is global. This paradox only arises if we assume that information can be dropped entirely over the horizon. But information is a pattern, and a pattern can't be dropped, it's already everywhere. A black hole doesn't destroy information. It's simply the last place we tried to shove it. I must say honestly, this isn't a new quantum gravity. It's not an information extraction mechanism. It's a conceptual shift. But sometimes in physics, the main thing isn't finding the answer, but asking the right question. Perhaps we've simply been looking for a black cat in a dark room for too long.